Okay, welcome to example 9. We have a problem that involves a uniform field. We have electric field here, 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 here. This is uniform because it's equally spaced um, between these two plates. This must be hooked up to a battery. One terminal is positive, the other one terminal is negative. And we have an electron that's projected horizontally and being deflected at this being deflected along here, this path that's curved like a parabola. So this is kind of a projectile motion problem involved with electricity. What we're trying to find is the magnitude of the electric field in this problem. So let's start off with this initial velocity, which is 5.00 times 10 to the power 6 meters per second. We know the vertical distance it goes up is 1 centimeter divided by 2 because it's starting midway, so that must be 0.5 centimeters. And the horizontal distance it's traveling is 2 centimeters. Okay. So what we're trying to do is we have to find the electric field. Now the electric field is the amount of electric force per unit charge. Now Q in this problem is Q for an electron, which is 1.6 times 10 to the power negative 19 coulombs. It's negative, but we are only looking for the magnitude. The force, how are we going to find that force? Well, my guess is we can go back to our dynamics and recall that force equals mass times acceleration, and so hence we would need to know the mass of an electron. So the mass of an electron is 9.11 times 10 to the power negative 31 kilograms. Now, to get the force, we know the mass, but we need to find the acceleration. And to find the acceleration, we were trying to find this vertical acceleration upwards. So this is really a sub y. Vertical acceleration can be calculated by using, let's see here, v squared. Well, I guess we don't know the final velocity. Maybe v or delta y equals v0 yt plus 1/2 ayt squared. So that will get us our vertical acceleration, assuming that the initial vertical velocity is 0 because it's projected horizontally. So, but to get that, we have to get the time. And that's where the horizontal distance comes in. Delta x equals the horizontal speed, v0x, which is actually v0, because it's completely horizontal here, times time. So, thinking backwards here, if we could find the time from the horizontal displacement and the horizontal speed, then we could find the acceleration from the vertical displacement and the time that we found earlier. And if we know the acceleration, we can find the force. And if we can find the force, then we can find the strength of the electric field. So let's go ahead and do that. Delta x equals v0x times t. T would be equal to the horizontal distance divided by the initial speed, v0, because v0x equals v0. And so our horizontal distance is 2 centimeters, so that's 0.02 meters, divided by 5.00 times 10 to the power 6 meters per second. And that gets us 4 times 10 to the power negative 9 seconds. So that's how long it takes to go across the plates. Okay, now we know that the time that it moves horizontally is the same as the time that it moves vertically. So let's now use our vertical displacement equation. Delta y equals v0yt plus 1/2 ayt squared. The initial vertical velocity is 0 because it's coming in horizontally at the beginning. And our vertical displacement is half of 1 centimeter, which is 0.5 centimeters. So this is 0.005 meters equals 1/2 times the vertical acceleration times the time of 4 to the power of -9 seconds quantity squared. And that will give us an acceleration of 6.25 times 10 to the power of 14 meters per second squared. So now that we know the acceleration, we can find the vertical force, which is force equals mass times acceleration. Mass of an electron is 9.11 times 10 to the power of -31 kilograms times the acceleration of 6.25 times 10 to the power of 14 meters per second squared. And that will give us 5.69 times 10 to the power -16 newtons. And then our last step now is to find the electric field by taking the force and dividing by the charge of an electron. So that force is 5.69 times 10 to the power -16 newtons divided by the charge of an electron, which is 1.6 times 10 to the power -19 coulombs. And that gets us an electric field of approximately 3,559 newtons per coulomb, which we can say is roughly 3,560 newtons per coulomb. And that's it for example number 9.